Morning is Mathieu Lauriere from Shanghai, and his talk is about the information cost of quantum memoryless protocols.
Thank you for the introduction, and I would like to thank the organizers for inviting me to this very nice conference, and thank you to everyone for coming this morning. So indeed, I will talk about the information cost of quantum memoryless protocols. And this is based on a joint work with André Chailloux and Jordanis Kerinidis, both in Paris. And actually, this paper has a quite long story because we started working on this at the beginning of my PhD, and then it took a very long time, and there were many chapters in this paper. But basically, in the end, the idea will be to study some specific class of protocols, so quantum protocols, where you have two players who communicate in order to compute some function, let's say. So there will be a classical output and classical inputs. But you have quantum resources to do that, so quantum communication. However, here we will be interested in memoryless protocols, and what we mean by memoryless is that the protocol cannot use working registers or private memory. And the goal will be to say something about the information cost of such protocols. So in the introduction, I will spend some time on the setting, so quantum communication, and also the definition of quantum information cost, because I believe it's not obvious what we mean by QIC. And then there will be several results that I will present. The first one will be a characterization of quantum information cost for the end function, and then some other results where you try to extend the model by adding coins, so either any possible private coins or just what we call one-shot coins. So first of all, the model. So let me start with the classical setting, because I believe in the classical case we have a better intuition. So let's say you have two players, say Alice and Bob. Alice receives some n-bit string x, Bob receives some n-bit string y, and they want to compute some function. They know, both of them know the function, some function f, of x and y. So since Alice doesn't know y and Bob doesn't know x, they have to communicate in order to compute this function. And there is a certain number of rounds of communications, and they want to do that efficiently. So how do you measure efficiency in such protocols? There are at least two measures. The first one, maybe the most obvious, is the communication cost. So it's the amount of bits that have been exchanged during the protocol between the two players. But you could also be interested in the information cost, which is the amount of information that has been transferred during the protocol. And there are different notions of information cost. But for example, let's say you want to measure how much Bob has learned about Alice's input and how much Alice has learned about Bob's input. And it turns out that this is always smaller than the communication cost, because you cannot transmit more information than the length of your message somehow. And as a consequence, information cost provides a lower bound on communication cost for a given protocol. And if you are interested in, let's say, a measure of complexity for a function, then you can minimize over protocols. So you can take the protocol with the best communication cost and the protocol with the best information cost. And information complexity will still be a lower bound on information complexity. And so if you care only about communication complexity, still information complexity could be useful if you want to prove that the problem is hard for communication complexity. So now let me try to be a bit more precise. So at the beginning, Alice has x and Bob has y. So let's say these two boxes are what they have in their memory. At the beginning, Alice prepares a message, m1, which is just a function of x. Let's say here there is no randomness, to simplify. And we want to measure how much information Bob is learning by this message. And here we would like to say that this is the information that Bob is learning about Alice's input, so x, condition on what he already knows, because we don't want to count many times the same information. So for this first message, it's easy. We will just write that the information cost of the first message is the mutual information between m1 and x, so how much m1 reveals about x, but you condition on what Bob already knows, which is here it's only y. And here, the notation I is the conditional mutual information, and it relies on H, the Shannon entropy. Now, for the second message, Bob prepares M2 using Y and M1, because now he knows M1, and he keeps a copy of M2. And then, same thing, you write the conditional mutual information, how much information M2 reveals about Y, condition on what Alice knows. And Alice knows X and the first message. And then you keep doing that until maybe N round, let's say. So that's the classical structure, let's say, for classical protocol. So in this setting, just to summarize, what now is usually accepted as the definition of information complexity or information cost for a given protocol is a sum over all the rounds of the information that the receiver learns about the sender's input, conditioned on what the receiver already knows, so the previous messages and his input. And so as I've mentioned, it is a lower bound on communication complexity. Actually, it's a quite powerful lower bound. And it has many nice properties. One of them being that it is exactly equal to the amortized communication complexity of a function. So if you want to solve many copies of the same problem, then you will get communication equal to the information complexity. So now, what about the quantum case? So before moving to a quantum setting, let me rewrite yet once again, in an even more formal way, the model of classical communication using somehow some circuit notations. So let's say at the beginning you have an input distribution, mu, and you pick some input x, you give it to Alice, you pick some input y, you give it to Bob. And then Alice will generate the message, first message, based on x and maybe some shared randomness, let's say here. And then she sends it to Bob, like this. And then Bob receives M1, and he generates M2 by applying some function. So here we don't care about the computational power, we just anything that you can compute. So M2 will be a function of M1, the shared randomness, and Y, let's say, etc. And then he sends M2 to Alice, and then they continue until one of the two players can answer and give the output, which should be the output of the function, except if you allow some error. So now in the quantum setting, I will use the following notations. So here, again, we will care about classical inputs, quantum protocols for classical inputs. So you have a quantum encoding of the classical inputs according to some distribution mu, and you give the x part to Alice and the y part to Bob. And then, let's say Alice starts, so she will apply a unitary operation on x and maybe some shared entanglement. And she will generate M1, and there will be some other part of what she's generating, which I will denote by A1. And she keeps this as a private memory. Maybe she can use it later. And let's say she also keeps a copy of X. Okay, without loss of generally, let's assume that she keeps a copy of X. And then Bob receives this quantum state, M1, and he applies a unitary. And he generates M2 plus some B2 that he will keep, etc., etc. So here AI and BI are the private memories of the players, and UI is some unitary operation. So in this setting, how could we define information complexity? So let's use the same intuition, for example. So this is something that we did simultaneously to the other notion of quantum information cost that I'm going to present in the next slides. So let's use the classical intuition. Then it's tempting to say, let's sum over the rounds. And for each round, we count how much information the message reveals about the other player's input, conditioned on what the receiver already knows. So here now, BI is a quantum state, private memory. In the classical case, it would be just all the previous messages. But in the quantum case, we cannot assume that the players made a copy of the previous messages because of the no-cloning theorem. So there is some private memory. We are not sure what is in this memory, but there is something. So we condition on this. And now I is the QCMI, right? Quantum conditional mutual information, based on Feynman entropy. And I will denote this by CIC, which is not to be confused with the classical IC, but it's a classical input quantum information cost, because it is defined only if you have classical inputs. And we can show, this is in a joint work with Jordanis Kerenidis, François Le Gall, and Mathis Renella, that CIC is a lower bound on quantum communication cost for any protocol. And so since we measure how much information the receivers learned about the other player's input, this has natural applications in terms of privacy. If you want to measure how much information has been leaked from one player to the other player, let's say. And for example, we have shown applications to private information retrieval. But simultaneously, Dave Touchet proposed another definition, which is slightly different. It's more general, so it works for any input, even for quantum tasks. But here I will write it only in the case of classical tasks. So the main difference is that there is a purification register denoted by R. So the players cannot access to this register, but then the whole state is pure. Basically, the input state is pure. And so the players run some protocol based on unitary operations as before, and they have some private memories as before. But the only thing is that you take into account this reference register when you want to measure the information that is transmitted. And the way the definition works, so denoted by QIC for a given protocol pi with input state rho, is that you measure the information revealed by MI about the reference register. And you condition on the same thing, which is the knowledge of the receiver. So here you see maybe it's not obvious at first why you put this reference register R in the definition, but it turns out that this definition is a natural candidate for the quantum counterpart to the classical definition of IC that I've presented in the first slides. And one of the main reasons is that it has many nice properties, and maybe one of the most important is that QIC characterizes the amortized quantum communication complexity. So this is the only property I have mentioned about the classical IC, and this is shared by the quantum IC in the quantum setting. And then there are other many nice properties. And another good thing is that it is an even tighter lower bound on QCC, in the sense that it lies between CIC, so the definition in the previous slide, and quantum communication complexity. So if you want to get a lower bound on quantum communication complexity, then it's better to use this notion rather than this one, because it will give a tighter lower bound. So it has natural applications in terms of communication complexity for lower bounds. And for example, it has been applied to the disjointness problem by Buhrman et al. And Davies, one of the authors. So now we have two definitions. Either can we say something better than just this inequality here? When is it tight and when is it non-tight, etc. So actually, if you want to, in some sense, complete the picture of the relationship between QIC and CIC, it turns out that you can introduce a third quantity. Well, of course, you can do that. CRIC is just the difference between QIC and CIC. But then how can you interpret this difference between the two terms? So in fact, you can rephrase the CRIC, not just as a difference between the two quantities, but you can write it in this way. So you see that it's very similar to the definition of CIC. So you sum over rounds, and you use the conditional mutual information condition on this part, and you measure how much the message reveals about the other part, the input of the other player. Now, what is the difference between this line and this line? You see, it's very similar, except that this term used to be here, and this term used to be here. But now you see that we sum over odd rounds. So for example, take the first round. Okay, Alice is sending the message. And we measure how much MI reveals about Y, which is the input of the other player, conditioned on what Alice knows. So in some sense, we reverse, and that's why there is an R here. We reverse the intuition, and we say, OK, how much the message reveals about the receiver's input. OK, the proof of this relation, I mean, why you can write QIC as these two quantities. The sum of these two quantities is based on what we have called an information flow lemma, which characterizes how much information is transmitted in a quantum protocol, but not only how much information is learned, which is measured by CIC, but also how much information is forgotten at each round. So this is the CRIC part. And in the classical case, for classical protocols, this term always disappears because nothing is forgotten, because you always keep a copy of previous messages. So you never forget anything. You never need to forget anything somehow. But in the quantum case, since you cannot make copy, for example, Alice will send something to Bob, and then Bob will send the same message back to Alice. And if he didn't make a copy, then he's forgetting what he has learned before. So you cannot assume that he's making a copy, and so you cannot assume that there is nothing forgotten. And so then you may wonder if forgetting is useful or not, because it seems that it's something useless to forget information. But actually, we have shown that there are some examples. So the disjointness problem, for example, where if the protocol does not forget information, so if CRIC is equal to 0, then you cannot achieve any quantum speedup. So in other words, if you want an efficient quantum protocol, by efficient I mean better than a classical one, then you have to forget information. And I think, well, at least to me, it's not very intuitive, because it seems that when you forget information, if you take a protocol and it forgets information, then you have to send this information again, because it has been forgotten. Let's say if Bob forgets some information, then Alice has to send it again, let's say, for later use. But actually, sometimes this is the best thing to do, and it's actually very useful. So now, yes, we understand better the relationship between these two quantities, QIC and CIC, and the gap between them is exactly the cost of forgetting information. And sometimes this cost is non-zero, and it is useful to take it non-zero. Now, we will consider a specific class of protocols, which we call memoryless protocols. So what do we mean by that? So let's take again the same notations like before, the same scheme. So, but now the difference is that when Alice applies the first unitary, U1, she generates first message, M1, quantum state, and she keeps a copy of X. X is classical, so that's fine. And then there is nothing else in her memory. There is no private memory that she keeps for later. And same thing for Bob. No private memory, only the input, Y, etc. And then they iterate. And now the question is, what can you do with these kind of protocols? So of course, it's a very restricted model, because you don't have memories. But it is still an interesting subclass of protocols, I think, for the following reasons. So the first one maybe is that such protocols would be easier to implement physically, because you don't have to preserve the correlations between the message and the working registers. So you don't have to worry about that. You just have to send a quantum state, and it should be easier to implement. Then there are also some theoretical motivations. For example, most non-protocols are actually of this form. For example, if you take the famous protocol of Buhrman et al., or the protocol of Klartag and Regev, and many other protocols are of this form, probably because it's simpler to think about such kind of protocols, because again, you have only to think about the messages. And then a third motivation, more recent maybe, is that it has been used in the construction of Bell violations. So there is a recent paper by Buhrman et al. Where starting from a memoryless protocol, it's not phrased like this, but starting from a memoryless protocol, you can construct a Bell violation. So there is a general construction. Actually, in the papers, they consider a general protocol, communication protocol, and then they convert it into a memoryless protocol. And there is a quadratic loss because of that. And then they work with this memoryless protocol. But if you start directly with the memoryless protocol, then you can construct a Bell violation. So, and another good thing, which will make our life simple, is that in this case, QIC of a given protocol, so the quantum information cost based on Dave Touchet's definition, is exactly equal to 2 times the CIC that we introduced before. And this is because the CRIC term, so QIC should be CIC plus the information forgotten, and the information forgotten is exactly equal to the information that you learn, because at each round you have to send back something, and you keep nothing. So you forget exactly as much as you have learned somehow. And that's why there is this factor of 2 here. So this corresponds somehow to one of the 2 extreme cases in the inequalities before. And in other words, it means that you just need to study one of these two quantities to get a bound on the other one here. And here we will be interested in one specific function, at least for the next few slides, which will be the AND function. So it's just you have two inputs of 1 bit, and you want to compute the AND. And while studying this function, you have many motivations. One of them is that this is a building block for more complex functions. For example, the disjointness functions. So here you have two inputs of n bits, x and y, and you would like to know if they are disjoint in the sense that there is no bit, no index where x is equal to y, or xj is equal to yj is equal to 1. Okay, if this does not happen for any j, then you say that the two inputs are disjoint. And you see that you can write this as an OR, or the negation of an OR of many AND. And this is useful because it has been used in the classical and in the quantum setting to derive lower bounds on the communication complexity of the disjointness function based on the information complexity of the AND function. Yeah, so you want to reduce the disjointness to the AND function, but also you change from communication complexity to information complexity. And this has been used, for example, in this paper by Yosef et al. In the classical case, and then in the quantum case by Raoul Jain et al. And what is the construction, let's say at a high level? So, because this will serve as a motivation for the rest of the talk. So you would like to take a protocol for disjointness and convert it into a protocol for the AND function. And then you could argue that this protocol cannot be too efficient, and then the original protocol for disjointness cannot be too efficient. But when you want to convert a protocol for disjointness into one for the AND function, you see that instead of having n-bit inputs, you should have just inputs of 1 bit. So to do so, you have to embed somehow your 1-bit input for the AND function into n bits input. And then you need to relate the information complexity of AND to the communication complexity of disjointness. And when you want to do that, actually you work with a certain input distribution where you generate the missing inputs in this embedding. And when you generate these inputs, they should be generated according to some distribution that does not bias the fact that you want to actually compute. This is the important part. So you take a 1-bit input and you embed it into a large input, but actually you would like the large input to be not so relevant. The only thing that should be relevant is your input that you have at the beginning. So there is a certain input distribution that is important for this construction. I'm going to explain now what this distribution is. So I will denote it by U naught for x, y, and here x and y are just 1-bit inputs. And basically you give 0 weight to the 1, 1 input, and then you give a uniform weight to the other inputs. So 0, 1, 1, 0, 0, 0. Of course, if you know this distribution, then the answer is always no for the AND function. But the point is that you don't know this distribution, and you would like to take a protocol that computes perfectly the AND function and studies the complexity of this protocol under this input distribution. Because again, it will be useful in the reduction from disjointness to AND. And what we can show is that for memoryless protocol, the QIC of AND is characterized by this ratio, log k over k, when you have k round of communication. Okay, so we restrict the model. We consider only k rounds of communication, and we would like to know how much information has to be revealed in the protocol. And the amount that has to be revealed is exactly log k over k. Again, this holds for memoryless protocol. And the proof of the upper bound is explicit. We have an explicit protocol. And this was already given by Jain et al. And written explicitly in this paper of Buhrman et al. On the disjointness function. So the upper bound is explicit. It's already known. And it is already a memoryless protocol. although it was not used specifically in the context of memoryless protocols. For the lower bound, we need to work a bit more. But the approach is analogous to this paper of Jain et al., except that they get a bound of 1 over k because they are working with general protocols, not memoryless. So if you allow your protocol to have some memory, you get 1 over k. But what we show is that if you restrict your protocol and you constrain it so that it has to be memoryless, so no working registers, then there is a loss of log k, basically, where k is the number of runs. So I will skip the upper bound, and I will focus on the lower bound. So the main improvement will be based on some inequality in conditional mutual information. So what is known is that if you take a quantum message in a general quantum state, M, and you want to know how much it reveals on X based on, let's say, the fact that Bob has input Y, then this, you can lower bound it by 1 minus the fidelity. And the fidelity of the two messages, one where you specify X is equal to 1, and the other one where you specify X is equal to 0. Yes, so let's say when you have input 1 and Y, you know the message. When you have input 0 and Y, you know the message, and then you measure the fidelity between them, and this will give you a lower bound on the QCMI. But it turns out that if M is a pure state, which will be the case in our setting because you have no memory, so M cannot be entangled with anything, it would be a pure state, then in this case, you can do slightly better than this. So what can you do more precisely? Well, if you have, let's say, a tripartite state, rho, with M in the middle, a pure state, and then X and Y are some classical inputs. In this case, you can lower bound the QCMI by this quantity, which involves the binary entropy, H2, of the square of the trace distance between the two messages. So you see these two messages are the same as this one. But this quantity is slightly higher than what we had before. So okay, it's just a technical argument. And it is based on some key lemma that relates just the mutual information. So let's say now you forget about Y. Just the mutual information between X and M, you lower bound it by the binary entropy of this trace distance. Okay, so it's almost the same thing, but this one is simpler. It's just mutual information. Then you plug this into this quantity, and you will get the other inequality. So I'm not going to detail the proof of this. It's more a technical argument, but I will explain how we use it to improve the construction of Jain et al. That I've mentioned before. So how does this construction work? Well, so you start by noticing that, okay, instead of studying QIC, I will study CIC, but it's the same thing up to a factor of 2. And the intuition is slightly simpler because in CIC, you just measure the information about the input and not about the purification register. So let's start with the definition of CIC. And when you take the distribution U naught, so you know that you will not have the 1-1 input. In that case, you can rewrite it as this quantity. So you minimize over all possible protocols, and then you measure the information cost of the protocol, let's say pi bar. But under the distribution U naught, and you condition on the fact that the input of the other player is 0. Yes, and this equality here is true because you can forget the 1-1 input, basically. So when you take the point of view of Alice, you just need to know what happens if, let's say, the other player has 0, etc., and conversely. So you can rewrite CIC as this quantity. And now we would like to get a lower bound on these terms, or on the sum of these terms. So let me call AI each term. So if I is odd, this is just this QCMI condition on Y is equal to 0. If I is even, it's this quantity. How do we get the lower bound on these terms? Well, the argument is as follows. So basically, we will be interested in measuring the information, or here's the trace distance, between the different cases when you swap one of the inputs, when you change one of the inputs. So let me denote by bi the trace distance between what happens, the states of the messages when you change the input of Alice. Let's say if I is odd, and if I is even, you change the input of Bob. Okay, so when Alice sends a message, I is odd, we want to compare what happens if she has 1 or if she has 0. And the other player has 0, let's say. And then conversely for Bob. Then we denote by delta I the converse. If I is odd, then we fix the input of Bob to 1, and we change the input of Alice. And same thing if I is even for the input of Bob. Okay, so now we have two different quantities. And we can show that actually at the end of the protocol, so let's say you have k round, then delta k measures the error somehow that you make at the end of the protocol. And this error is always, well, let's say you have an epsilon error protocol. So this will be 1 minus, you can lower bound this by 1 minus epsilon if your protocol makes epsilon error, at most epsilon error. And you can also see, so this part is not so difficult to see if you assume your protocol makes epsilon error. The other inequality is more involved, so I'm going to skip this part because it's exactly the same as in the paper of Jain et al. But you can show that delta k, so delta at the last round, is actually bounded by the sum of the bi's, or 2 times this sum. And this inequality relies on well, some properties of the trace distance. So here it will be the triangle inequality and the unitary invariance. So it doesn't work if you take something else. I mean, it doesn't work with some other quantities instead of the trace distance. It could work with some other quantities, but yes, it's very specific. So now, what do we do with this bound? Well, we have to relate this to the AI that were introduced at the beginning. And here, we split the analysis into 2 cases. The first one is what happens if there is one AI, so let's say aj, for some j, that is large enough, larger than some constant. And here, I pick 0.4, so you will see why. But basically, if you assume that there is one aj bigger than some constant, independent of k, then the CIC of pi bar, which is the sum of the AI, will be in particular larger than this specific aj, so it will be larger than the constant, and then if you take k large enough, it will be larger than the bound that we are looking for, log k over k, for k large enough. Okay, so this was the easy part. Now what happens if all the AIs are smaller than this constant, for example, 0.4? Well, then the good thing is that in the region between 0 and 0.4, we have the concavity of this function. So we cannot show that it's concave on the whole interval from 0 to, let's say, 1. But on this restricted interval, it's true. And then you can apply some inequality related to concavity. And more precisely, you can show that the sum of the bi's, so bi again involves the trace distance, and then you can take this function, apply the concavity inequality, and you will get inside exactly the CIC. So this is because you will get exactly the sum of the AIs. And then you can conclude from that that since the sum of the bi's is lower bounded by 1 minus 2 epsilon, you can get the lower bound that you were expecting in both cases. In the case where the aj, there is one aj larger than some constant, and then in the case where all the AIs are small enough. And this is the place where we use the key lemma in the key proposition in the previous slide. Okay, this was the only technical slide. Now we'll go back to more high-level ideas. So just to summarize, we can show that the QIC or CIC is the same thing as theta of log k over k. Now we would like to turn to the more important question maybe, which is what is the quantum communication complexity of disjointness? Because as I said, you can sometimes you can reduce the QCC of disjointness to the QIC of AND. And now we have characterized this in the memoryless setting. So what is the memoryless communication complexity of disjointness? So we'll make a few attempts. So the first thing we can think about is try to reuse the quantum construction of Jain et al. And the construction works as follows. So you start with the protocol for disjointness, and you want to construct one for the AND function. But for the AND function, you have just 1 bit inputs. So you generate the other n-1 bits in superposition for each player. And then you get an input of length n. So you plug this in the protocol for disjointness, you run this protocol, and then actually you get with a specific input distribution for these superposed bits. And then you get the output which corresponds to your original input for the AND function. But the problem is that when you do that, you see, since you need to generate inputs in superposition, the players will keep some memory. So the construction does not preserve the property of being memoryless. So what we can do is we can try to go back to the classical intuition. If the closest possible idea, which was this paper in the quantum setting, doesn't work, maybe you can go back to the previous paper, which was in the classical case. And in the classical case, instead of using superposition, we use private coins to generate the other inputs. So Alice will generate n-1 bits with private randomness, and Bob will do the same thing with his private randomness. So what about allowing the players in the quantum memoryless setting, allowing them to use private coins, private classical coins? Yes, this would preserve the memoryless structure because it's not some quantum superposition, but maybe then we could look for a protocol for disjointness. Well, actually, this does not work because we can show that if you allow the players to use private coins, then there are some perfectly private protocols in the sense that if you take a function f, and you can construct a protocol, memoryless protocol, that computes this function exactly, and that leaks as a minimal amount of information, in the sense that the amount of information leaked by pi is just what you need to produce the output of the function. Because this is exactly what is leaked by the output of the function, so you cannot do less than that, because you have to at least answer to the question. And the reason why it works is because you take a protocol, let's say pi tilde, computing the function, and then you are going to construct another protocol that mimics this one, but except that before sending the messages, you encrypt them. You use your private randomness to encrypt the messages. So they apply some unitaries to encrypt their messages, and then they send them over. And they never decrypt. That's the point. So what happens? Well, if they had the same coins, then, well, I don't detail here the construction, but in our construction, you can show that if they have the same coins, then Bob would know how to output as in pi tilde, because their coins coincide. But if there is just one coin that is different, then actually they don't get any information about the other player input, and they cannot answer, so they just run the protocol again. And they do that until they get the same coins. So of course, the communication will be extremely large, but the information will be almost zero. So this yields a private protocol, which is, in some sense, it's a good thing if you care about privacy. But if you care about lower bound for quantum communication, then it's not that good, because basically CIC, QIC is just almost zero in this case. So it will not provide a good lower bounds on communication. So what we can try, maybe, is instead of allowing private coins in general, we can allow private coins that you can use just a little bit. What we mean by that is what we call one-shot coins. And one-shot coins are coins that you can use only once in the protocol. So let's say now you have Alice and Bob. They want to run a memoryless protocol, but they have access to private coins, except that these coins, each coin can be used only once. So in the classical setting, this is not a restriction. Actually, you can show that if you allow players to use coins only once, they can still do as much as what they can do with coins they can use any number of times. And you can do that even while preserving the information cost and the communication cost. So you start with a one-shot coin protocol, and you construct just you can mimic any randomized protocol with the same information cost and the same communication cost. But in the quantum case, it will not be so easy. So the structure of a one-shot coin protocol, memoryless, let's say, is that the players, at the beginning, they receive their inputs, so X and Y, but they also receive some set of coins that I denote by RA for Alice and RB of Bob. And these coins are, you can split them into, let's say, K parts, if you have K rounds. So Alice has RAI sub I for I between 1 and K. And at each round, she will use one part, and then she will not use it again. And what I mean by use is that when she applies the unitary to get Mi based on Mi minus 1, this may rely on Ra sub I, but not the previous or the later sets of coins. So what can we say on such protocol? So it's less powerful than allowing general private coins, but it's still better than not having coins. So it turns out that in this setting, you can show that if you start with, let's say, memoryless protocol, pi, with one-shot coin, then you can get another protocol without coins. So you can basically get rid of the coins without leaking, without adding too much information. Yeah, so if you want to remove completely the coins, it seems that you should reveal more information, but actually not too much. So more precisely, you can construct a protocol pi prime without any coin, such that the CIC of pi prime is bounded by the CIC of pi with a small overhead, a small factor. And this factor is logarithmic in the number of rounds and logarithmic in the original CIC of pi. And just a few words for the proof. What we use is the fact that when Alice wants to send her message, she will apply a unitary to avoid leaking too much information before doing that. Then she applies this unitary, she changes a little bit the message she's going to send, and then she sends the message. And the analysis shows that you can get this bound. But still, the problem will be that if you allow only one-shot coins, this is not enough to reproduce the construction of Barrios F et al. In the classical case for disjointness, because when you generate the other inputs, the n-1 inputs for disjointness, you are going to use them maybe many times, not just once in the protocol. So a priori, one-shot coins are not enough for reproducing the disjointness result. So as a conclusion, we have formalized the model of memoryless quantum communication complexity, which was already around in many papers, but we have just extracted this formalization. And we were able to characterize the memoryless quantum information cost theory of the on function. So for one specific problem, at least we're able to characterize the QIC in the memoryless setting. Then we have shown that when you allow classical coins, private coins, you can get perfectly private protocol, which is good for privacy and not so good for lower bounds on communication complexity. So it depends what you care about. And then if you do one-shot coins, this does not change too much the memoryless information cost. Maybe a few open questions. So of course, I have mentioned the disjointness problem as a motivation for this work. We get some other results, but the question is still open for the memoryless communication complexity of disjointness. In particular, is it higher than the general communication complexity of disjointness, or is it the same? Can we find the memoryless or characterize the memoryless communication complexity for other problems, not just the on function? And maybe also in the introduction, I have mentioned this relation between QIC and CIC and the cost of forgetting. And are there other problems for which we can show that forgetting is useful, or is it just specific to one problem? Thank you.